Hello and welcome back again. This is our third lecture in Chapter 2. Today we're going to talk about constant acceleration. And we're going to end this lecture with doing an example problem of constant acceleration. These are a big part of what's going to be on our first test. We're going to spend a lot of time in class working on these, so make sure that you understand this. Go back and review this problem again if you need to. Before we get to that, let's talk a little bit about constant acceleration in general. Now let's start with a simple situation. Imagine that we have a race between a Volkswagen Beetle and a Porsche to see which can achieve a velocity of 30 meters per second in the shortest amount of time. So we can make a table of each car's velocity over time and make a graph of velocity versus time. Now we can't really say that one is necessarily faster than the other. That's not what acceleration measures. But we can say that one of them speeds up more quickly than the other. The one that speeds up more quickly has a larger acceleration. Just to remind you again what acceleration is the rate of change of velocity. When we have velocity changing at a constant rate, you're going to see a straight line like we have for both of these on a velocity time graph. If we calculate the slope of this line, it will give you the acceleration. In this case, the slope of this line, the change in velocity, which is on the y-axis, would be 30 meters per second divided by 6 seconds for the Porsche. What would it be for the VW? Well, it still ends up at 30 meters per second, right? But it took 15 seconds for that to happen. So we could say that the Porsche has an acceleration of 5 meters per second squared, while the Beetle only has an acceleration of 2 meters per second squared. So even though they eventually reached the same speed, the Porsche got there a lot faster. What are the units of acceleration? You may have already noticed that acceleration is measured in units typically of meters per second squared. Now what that really means, it's meters per second. We usually just abbreviate that meters per second squared. Because what acceleration means is tells you how quickly the velocity is changing. So for example, if you have an acceleration of 1 meter per second squared, that means the velocity changes 1 meter per second every second. So if it starts at 0, after 1 second, it's 1 meter per second. After 2 seconds, it's 2 meters per second, and so on. We often talk about average acceleration as well. Now, when something has a constant acceleration, its average acceleration is going to always be the same as the instantaneous acceleration at every point because it's constant. If not, though, you can still find an average by taking the change in velocity between two time points. And you can find that in the same way that we would if it was constant. Also point out that acceleration, like velocity, is a vector and it does have both a magnitude and direction. And we've already talked about how to find the direction of the acceleration and what that direction means. So let's review that for just a minute. Here's a quick question showing a motion diagram of a car speeding up and moving on a straight road. What direction is the acceleration? I'll give you just a second to think about this. Did you pick that the acceleration is negative? That's correct. Why is it negative? At first glance, you may see speeding up and you may think that means it's positive acceleration. But just as we talked about in class, if something is speeding up, that does not necessarily mean it has a positive acceleration. We can look at the picture and we can see that the velocity arrows are getting bigger in this direction. The acceleration is always going to point in the direction where the velocity is getting bigger. So that's in the negative direction. Now, how can it be speeding up and have a negative acceleration? We'll notice that at every point the velocity is also negative. And just as we talked about in class, if you have a negative velocity and a negative acceleration, that means that you are by definition speeding up because velocity and acceleration are in the same direction. Let's look at another example. Also kind of going back to review what we did in class. Here we have a velocity time graph of a basketball player, starts at the left end of the court and moves with the velocity shown in this picture. So we want to try to figure out from this, what would his motion diagram look like? How is he moving? And then an acceleration versus time graph. So let's just talk about in words and write down what he's doing in the different parts of this graph. We really have 3 sections to think about, from here to here, from here to here, and then from 9 to the end. So during the first 6 seconds, he's moving with a positive velocity, and he's clearly speeding up. Because his velocity is getting bigger. During this time, he's moving with a negative, not a negative velocity, still a positive velocity, but it's a negative acceleration. So he is slowing down as he gets closer and closer to 0. Now this is an important point right here. What happens right here when the velocity changes from positive velocity to negative velocity? Whenever your velocity changes direction, he turns around. And then what happens in this part, now he has a negative velocity that's becoming more negative. So he's speeding up in a negative direction. So we need to show all of these parts on our motion diagram. Like this. Remember we said in the first part, he's speeding up. So we show that these velocity vectors get bigger and bigger and bigger as he gets up to 6 seconds. So we have a positive acceleration, positive velocity. What happens after that? Then he starts slowing down, right? He's still going in a positive direction for a while, but we now have a negative acceleration. And notice that this acceleration is bigger than the first one. We could tell that on the graph as well because the line was steeper. The slope is bigger. At 9 seconds, he turns around. We show that here. We can draw these arrows just coming down underneath like this. And then it continues to slow down with the same negative acceleration during the entire time. What does that look like on a acceleration versus time graph? Well, we can calculate the slope of these 2 lines. The slope of the first line would be 6 meters per second over 6 seconds to give us a positive 1 meter per second squared for the first 6 seconds. For the second 6 seconds, we have minus 2 meters per second squared. So it switches from positive to negative. Notice that it doesn't do anything right here at 9 when the velocity graph crossed 0. So just because the velocity changed direction there, that doesn't mean the acceleration changed direction. That's going to come up again and again in many problems. So just to reiterate one more time again, the sign of the acceleration does not tell us whether the object is speeding up or slowing down. Here we have the same acceleration during the whole time. During the first part of that motion, it's slowing down. Then it turns around, then it's speeding up. But the acceleration stays negative for the whole time. Okay, now let's turn our attention back to specifically constant acceleration. How do we solve problems when we know that we have a constant acceleration? Well, we can use some of the mathematical relationships that we've already derived, and in particular some of the graphical relationships between things like velocity, displacement, and acceleration to derive some equations that we can then use to solve a variety of different types of problems. So suppose that we know the object's initial velocity. We also know that it has a constant acceleration over some time interval. We can then find the object's velocity later. We can also find the object's displacement. We can find a lot of things about the motion, and that's what we're going to look at next. So to figure out how we would start to derive these equations, let's think one more time about what constant acceleration looks like on a velocity time graph like this. So as we've seen several times, on a velocity time graph, when you have a constant acceleration, you're going to have a constant slope. And remember, what does the slope tell you of a velocity time graph? It tells you the acceleration. What does the area under the graph tell you? It tells you the displacement. These 2 things are going to tell us everything we need to know and allow us to derive some really useful equations. Let's see if we can use that velocity time graph to derive now some really important equations that we will use throughout the rest of the course. I'm going to redraw the graph first. Right, so let's assume we have constant acceleration, so we have a straight line. In that case, we know that the acceleration equals the slope of that line. All right, so acceleration, again, we're just going to talk about x direction here, although this could be applied to other directions as well. The slope would be the change in the y values, which is VF minus VI, divided by the change in the x values, which if we come to our graph, we're just going to call that delta t. Usually t starts at 0, but not always. We can rearrange this by multiplying both sides by delta t, and we have ax times delta t equals VF minus VI. We can add VI to both sides to get the standard form that you usually find this equation, which is VF equals VI plus A times delta t. Now this is one of the famous kinematic equations of constant acceleration. The first one. There are two more that we're going to derive. The second one we can get from looking at the area under the graph. Remember, this area under the graph is equal to the displacement. So two pieces of information that we can get from a velocity graph. Displacement equals the area or the integral of this velocity curve function. Displacement is delta x. The area. Now how do we find the area? We can break this up into two individual areas. We have a rectangle and we have a triangle. We can add those together to get the total. So the rectangle area is just like the area of any rectangle. The height of the rectangle times its length. The triangle is 1/2 the height of the triangle, which would be VF minus VI times delta t. Now you can leave it like this. This is perfectly acceptable, but it's not the standard way that we usually see this equation written. So to do that, we need to come up here and notice that we had this that said that acceleration times delta t equals VF minus VI. So VF minus VI, we can replace that with AX times delta t. And we can rewrite this equation as delta x equals VI times delta t plus 1/2 AX delta t times delta t again. So delta t times delta t would be delta t squared. So we have displacement equals initial velocity times the time interval plus 1/2 acceleration times delta t squared. Now keep in mind also delta x is the same thing as final position minus initial position. So we commonly see this written like this. Final position equals initial position plus initial velocity times time plus 1/2 acceleration times delta t squared. This is our second famous kinematic equation. And we can put these two together and do some algebra to eliminate time, which I won't go through all the steps that are involved in that. But if we combine these two equations together, eliminate the time variable, we can get a third equation, which is sometimes also very useful, particularly in situations in which we don't know the time. This then is our third equation. Now, these equations are some of the most important and most useful ones that we will derive all year. We will use them extensively. But remember that we got these equations directly from a velocity graph that was drawn for an object that had a constant acceleration. So that means that while these are very useful and very powerful, they are not universal. They only apply when you have a constant acceleration. So in situations where the acceleration changes, we have to use some other techniques, which we'll talk about later. So just to review everything that we know about constant acceleration before we do an actual problem, we can model constant acceleration on a motion diagram. It looks like this. We have the velocity vectors getting longer by the same amount each time. On an acceleration time graph, it looks like a horizontal straight line. On a velocity time graph, it looks like a straight line that is not horizontal. The slope of that line is equal to the acceleration. And on a position time graph, it looks like a parabola where the slope is changing as you go. Mathematically, we can use the velocity time graph to derive those three equations. Notice these right here are the same three equations that I just derived on the previous page. They just use s in place of x. We can substitute in x or y or any variable that we need to determine what direction we're moving in, and these equations are still always the same. But again, just like I said, this is important. This is a very powerful model, but it will fail if the acceleration changes. So everything we've done, we can only use these when we have a constant acceleration. So now let's turn our attention to how to actually solve a problem when we know that we have constant acceleration. First of all, determine if in fact the object in that situation really does have constant acceleration, because you cannot use all the equations of constant acceleration unless that's true. So make sure that it is before you start. Once you know that it is constant acceleration, then draw a pictorial representation. For right now, that's a motion diagram. Label everything that you know, identify things that you don't know, give variable names to all the information in the problem and all the things that you may or may need to find. Use a graphical representation if it's appropriate. That could be position time graph or velocity time graph. In my experience, velocity time graphs are very, very helpful for these types of problems, and I'm going to show you how in just a second. The mathematical representation is then based on those three kinematic equations. Sometimes you can solve the problem directly from the graphical representation. Sometimes you can use the mathematical representation. And sometimes you can use either one, whichever you feel more comfortable with. Finally, at the end, check that your result has the correct units and significant figures. Make sure that it's a reasonable answer, and make sure that it actually answers the question. Sometimes people do a lot of work and then they don't do the last step to actually answer whatever the question is asking. So make sure that you have done everything that the question asks for. Let's look at how to apply this then to a real problem. This says that Fred is driving his Volkswagen Beetle at a steady 20 meters per second when he passes Betty sitting at rest. Betty instantly begins accelerating at 5 meters per second squared. How far does Betty have to drive to overtake Fred? So what we have here are two objects moving. One has constant velocity, one has constant acceleration. So let's draw a motion diagram of each of them. So I'm going to start with Fred. Fred is going at a constant 20 meters per second. He is not changing. Right? He's going the same. He doesn't speed up or slow down. So label this Fred. His velocity the entire time is 20 meters per second. Now Betty comes along and she's at rest. But as soon as she sees Fred, she decides to start taking off after him. So she starts out very slowly, but she speeds up. And at some point, she catches Fred. We know that she's accelerating this way. She has a positive acceleration of 5 meters per second squared. Now, what else do we know about this problem? Well, we need to pick a origin. I'm going to say the origin is the point where Betty first passes Fred. So that means that Betty and Fred both have an initial position of 0. And I'm going to say time is 0 there too. Now, we know that Fred's velocity is the same all the way through. So that is his initial velocity. But for Betty, we're going to say she has an initial velocity of 0 as well. Because it says up here in the problem, at rest. That's the key words. It doesn't say initial velocity equals 0, but it says she's at rest, which means 0. At the end here, we don't know Fred's final position, and we don't know Betty's final position, and we also don't know the time when they get to that final position, and we don't know Betty's final velocity. So each of these things are unknown. So we have several things that we don't know. However, if we think about the problem, if Betty is going to pass Fred, then the final position that Betty has to equal the final position that Fred has. And the times have to be equal too. They have to be at the same place at the same time. So we know that these two things have to be the same, which also means that the displacement of Betty has to equal the displacement of Fred. So this is our starting point for the problem. Before we do anything else, we want to define everything that we are given. We want to identify what those variables represent, and we want to identify what unknown things we may need to find. So the problem asks us for how far does Betty have to drive. So that's asking us for this delta x. But in order to do that, we may have to find some of these other unknowns. So it's good to identify that those are also things that we may need to know as we proceed. So once we've gotten this pictorial representation first, we've identified everything, where do we go from there? Well, there are two ways that we can go about solving this problem, and I'm going to show you both ways. First, we can solve this using a graphical method. Velocity time graphs are your friend for doing this. So if we try to draw a velocity time graph for Fred, it's going to be very simple. Right? It is a constant 20 meters per second until he stops at some final time. Now if we draw a velocity time graph for Betty, hers is going to be different. She starts at 0 and she increases her velocity for the same amount of time. That's the same final time. We don't know her final velocity when she gets there. Remember, that was one of the unknown things we identified. However, we do know the slope of this line, right? We know that the slope of this line is equal to 5 meters per second squared. Remember, we just said that the displacement of Fred and the displacement of Betty have to be equal to each other if she's going to pass him. Whenever they end up at the same place at the same time, that's when she passes him. So how do we find the displacement of Fred and displacement of Betty? Well, look at our pictures. Remember that the area under these graphs tells you the displacement. So the displacement of Fred is just equal to this rectangle, which is 20 meters per second times TF. The displacement of Betty is equal to this triangle, which is 1/2 VF times TF. Before we can set these equal, we need to get rid of the VF so that we can have the same variables. How do we get rid of VF? Well, remember, we have the slope equation. We know that the slope, acceleration, is equal to final velocity minus 0 divided by final time minus 0. Should be a t. And the acceleration here was 5. So we have 5 equals VF over TF. So that means that VF is equal to 5 meters per second squared times TF. And we can put that in here. And we can have that displacement of Betty is equal to 1/2 of 5 meters per second squared times TF, which would be TF squared. Now we know that this and this have to equal each other. So we can set those equal. We can have 20 TF equals 1/2 of 5 TF squared. Notice that we can divide both sides by TF. You can eliminate 1 TF on each side, and we can have 20 equals 1/2 times 5 is 2.5 TF. Dividing both sides by TF, or I'm sorry, by 2.5, gives you that TF is 8 seconds. Now, this is an answer, but is this the final answer? This is the great place where you want to go back and check to make sure that you really answered the question. Remember what the question asked. The question said, how far does Betty have to go? So we're not quite done. We figured out the time when Betty catches him, but not the distance. But once we have the time, we can come back up here and we have two equations for displacement. We can use either one of those to see how far they each go. And in fact, it's a good idea to use both of those. If they both equal the same amount, then that's a good way to check your work. So, see, the displacement of Fred was 20 meters per second times the final time, which was 8 seconds, or 160 meters. Now, what was the displacement of Betty? 1/2 of 5 meters per second squared times 8 seconds squared. That's equal to another 160 meters. These are the same. So how far does Betty have to go? 160 meters until she catches up with Fred. Now, is this the only way that you can solve this problem? Absolutely not. Next, we'll look at how to solve it directly using those three kinematic equations that we just derived. So let's examine the same problem again. We've already got identified what we know. We've already got our pictorial representation. What if you don't want to do it using the graph? Then you can use the kinematic equations directly. In this case, probably the most useful one would be the second one, which says that final position equals initial position plus initial velocity times time plus 1/2 acceleration times time squared. Now, we would need to write this equation out for both Fred and Betty. Because just as before, the final position of Fred has to equal the final position of Betty if they end up at the same place at the same time. So for Fred, he starts at a position of 0. He has a velocity of 20 meters per second. We don't know his time interval, but he has 0 acceleration, so this whole term is 0. For Betty, she also starts at a position of 0. She has 0 initial velocity, so the second term is 0. But she has an acceleration of 5 meters per second squared, equals times delta t squared. Now this and this have to be equal to each other if they end up at the same place. So we can rewrite that as a mathematical equation. 20 delta t for Fred equals 1/2 of 5, which is 2.5, times delta t squared. Now notice we're back to where we were with the graphs. We can divide each side by 1 delta t, divide by 2.5, and get that the time interval is 8 seconds. Sound familiar, right? Now we can take that and we can plug that back into either one of these equations to solve for the final position. Once again, I would advise you to do both. So for Fred, we would have 20 meters per second times 8 seconds equals 160 meters. For Betty, we would have 1/2 5 meters per second squared times 8 seconds squared equals 160 meters. So once again, as we would expect, we get the same answer. Two different ways. Now, do you have to do every problem using both ways? Of course not. I just want to show you both ways. In some cases, one may be easier than the other, or you may just personally prefer one to the other. As we do more and more problems, you'll get better and better at figuring out which way you like to do it. I'll try to do some one way and some the other. Our last step in every problem is to assess. Make sure their answer makes sense. So 160 meters, what we calculated, is about 160 yards. Because Betty starts from rest, it makes sense that she needs about 160 yards in order to catch up. All right. Now, does this mean that we definitely got it right? No. The purpose of this step at the end is just to make sure that your answer is not clearly wrong, right? If you calculated that she caught up with him in like 2 yards or 2 meters, that wouldn't make much sense because it's like right after he passed. By the same token, if it took like miles and miles to catch up with him, that didn't really make sense either. So it rules out things that are obviously not right, even though it may not completely tell you whether it is right. Tomorrow in class, we're going to spend the whole class period doing more and more problems just like this one. So come prepared. Make sure you remember these equations. Make sure you've studied this problem and thought about how to set up everything so that you'll be ready to go in the morning.